Alright, in this video we're going to talk about how to approximate some areas that we can find under curves, and we'll use specifically Riemann sums to do it. It seems like we're going to put a pin in this idea of antiderivatives that we were talking about in the previous video, but I promise we will circle back and make a connection between antiderivatives and these areas under curves. So this is where we're at right now. How are we going to approximate these areas? And then we'll introduce Riemann sums. It seems like it's a relatively short list of things to do on this video, but we'll see how that goes when we get into it. So first, the main thing that we might want to notice is that approximating area in straight edge shapes is actually pretty easy to do. We don't even have to approximate it. I can make a really weird shape here. And there are some really neat results that say if you have any sort of straight edge shape, you can always just draw triangles inside of it. And really, then, this is just 4 different triangles added up, and once we can find the areas of these 4 triangles here, we can add those things together and find the area of this weird straight edge shape. So that's cool. What we'll find, though, is that when we have a function, this is supposed to be f of x equals x squared plus 2, when we have a function like this kind of parabola here, we're going to have a curved shape, and that ends up being a lot harder to approximate areas. So this is the area we're thinking of. We've got this nice parabola here. It's shifted upwards. I'm only going to draw this portion of it because I'm just looking between x equals 0 and x equals 3. Let's just call this x equals 3. So if I draw my straight line going up, the area that I'm looking at now is this area right here. And this is a harder area to evaluate because of this curved parabola edge. Now, we could use some other known curved shapes to try and guess this thing. We know areas of circles, but what we'll find if we do that is that circles have a very specific kind of curvature, and it's different than parabolas. And so we can't even apply the formula for the area of a circle to something like this to try and cut out this portion or something like that. So this ends up being a lot harder of a problem than we may have guessed. So we got to figure out how we can actually do this. Oops, I skipped ahead a little bit too much. So there are a couple of ways of doing this. I'll probably just kind of show off a couple. Maybe I'll do this in green here. So an obvious way of doing it, I think, is to just try and approximate the area of this big rectangle here. And we wouldn't have to approximate that area as long as we know the side lengths. We could find the area of this rectangle and say yeah, okay, that's an approximation of that red area. That's a bad approximation though, right? It's way too big. Similarly, we could just draw a rectangle here. And we could say all right, well, what if we just did this? And again, that's not that good. But if we drew a trapezoid, maybe we could do a triangular portion here with the rectangle on the bottom, and we could find the area of this trapezoid by doing the same kind of straight edge business that we did earlier, right? Cut it up. Here's a triangle. Here's a rectangle. Find those two areas. Add them together. And then you could do a whole bunch of stuff where we say, well, what if we make a triangle? I'm going to get my straight edge shape back. Maybe we'll do this rectangle on the bottom again. But then what if we did a triangle here and then a steeper trapezoid where we've got another rectangle and a triangle, and then it looks like we've got another rectangle and a triangle. We could do something like this, and suddenly it looks like I've drawn an okay version of my shape, right? But what you'll notice is that the more detail we add, doing it like this, the harder it becomes to find all of the areas because we have to know all of the different side lengths and a whole bunch of different stuff here. So our goal is to just try and get a better version of approximating area, but we also want to not make it too hard on ourselves. We could draw hundreds of little rectangles and triangles and things like that in this region and try and get a pretty good idea of what's happening. But if we do that, we end up overcomplicating the types of areas that we're going to have to find. So the answer is that we're just going to use a whole bunch of rectangles, and we're going to be very clever about how we use them. So let me show you what I mean. I'm going to approximate this area, and again, I want to change this so that this is f of x. Oops, get rid of my straight edge shape here. This is f of x equals x squared plus 2. I'll draw this parabola again, just a portion of it, and I'll show you what I mean by saying use 4 rectangles. Let's say this is 3 right here, and this is 0, and we want to find this area. What I'm going to do is I'm going to divide this into 4 regions. The whole width now is divided up into 4 regions, and each of these regions is going to become a rectangle. So we're going to kind of draw like a bar graph. Maybe I'll go here, and I'll go all the way up here. And if we find the area of each of the rectangles, area 1, area 2, area 3, and area 4, then we can just say the actual area under our curve is pretty much just those 4 things added up. Now, finding these areas is not difficult if we make some decisions about how we're defining the widths and how we're defining the heights of these rectangles. Notice that if we want, we could say the widths are all just the same. So maybe I'll say constant width or consistent width. The width of each rectangle is going to be 3 divided by 4 because it's this total width of 3 units from 0 up to 3 divided equally into 4 rectangles. Now I need to find the height of each rectangle. So for each of these rectangles, it's going to be 3/4 times its height. And the heights of each rectangle, you'll notice, are seemingly defined by these points. And these points are points on our function. So maybe it looks like the height of this first rectangle is f of 0. And it looks like if this is, maybe I'll draw these in. So this is 3/4 right here. This is 3/2. This is, what am I looking at here? That would be 6/4, so 9/4. Or you can say 0.75, 1.5, 2.25, etc. These are the x values at all these border lines. It looks like this might be at like 1. Maybe. So we'll say, all right, that was f of 1. And then it looks like this one is f of 9/4. And this last one looks like it's f of 3. But again, since we have a function, we can go ahead and just plug all those values into our function, and we're going to get a width and a height. So our heights are just function values, or y values. All right, so go ahead and do this. Calculate all this stuff out. See if you can find these 4 function values by, again, plugging them into this function here, x squared plus 2. And then we just have to multiply all those function values by 3/4. We'll have a width and a height. That's going to give us 4 separate areas. So pause the video, give that a shot, see if you can do that. So hopefully you ended up with something like this. All of these function values are pretty easy except for maybe this one right here, right? 9/4 squared is really 81 over 16. And then when we multiply that, add 2, that's 81 over 16 plus 32 over 16. And so that's where this 113 over 16 is coming from. And then multiplying that by the width is really annoying. You get this ugly fraction. So I went ahead and just wrote it as a decimal. So all of these here are written out as decimals, and then we can see that our approximation of our area is just going to be 1.5 plus 2.25 plus 5. Oops, I forgot my 296,875 plus 8.25. And if you throw that into a calculator, you end up with 17.296875. So we can say, like, I don't know, maybe like around 17.3 or something like that. right? This is an approximation of the area under this parabola from x equals 0 to x equals 3. We cut this up into 4 rectangles, found the widths of each rectangle, found the height of each rectangle, and then that gave us the area of each of those rectangles and added it up. Cool. So what we're going to do is take that general idea and put it into this Riemann sum object here. We're going to use these Riemann sums to keep our structure of how we do this all consistent. So we have some definitions that we want to talk through, make sure that we can get all this stuff figured out, and then from there we'll go ahead and redo this problem using some actual Riemann sums. So first, we're going to define this idea of a regular partition. What we did at the very beginning was we took this little interval from 0 to 3, and we cut it into 4 subintervals. 1 subinterval, 2 subintervals, 3 subintervals, and there's our 4th one. A regular partition just says that all of these are equally sized, right? We said that each of these just were 3/4 units wide. Now that's not something that we have to do. We could cut this up into 4 subintervals where it ends up looking like this from 0 to 3, and maybe our first subinterval is like way up here and our second one is really small, and then we divide this one in half. So it looks like our first subinterval is pretty wide compared to all of them, and our second subinterval is not very wide. They all have different widths. A regular partition just says take this thing, divide it up equally. So delta x, the width of these, is really just going to be b minus a. That's our ending point minus our beginning point. That's our total width divided by n, the number of rectangles or subintervals that we have. And again, that's going to force these things to be equally sized. The actual thing that we're defining as the partition, though, is the x values. So for us, we said that was 3/4, 3/2, 9/4. So our our partition, might be 0, 3/4, 3/2, 9/4, 3. That's the thing that's going to get us all the way up to, cut this up equally and count up to 3. For this one, we might say something like 1.5, 1.7, and 2.6. I don't know. I'm just making these up. And so here's another partition. This is not a regular partition because the spacing in between the 4 numbers, or the 5 numbers that we have to split this up into 4 subintervals, is all different. All right, that's a lot of words, and hopefully you understand what I'm talking about here. This is the definition of a Riemann sum. There are other definitions of Riemann sums that you'll see, maybe. Some of them use a sigma sum notation. So maybe you'll see this every now and then, and you'll say something like k equals 1 up to n, and then you have f of x sub k star times delta x sub k. This notation is just a summation notation, and it basically means add up all of these terms where k can change from 1 to 2 to 3 to 4 to 5 up to n, however many you've got. This is really helpful to do when you have a lot of things that you're adding up and they all have the same form. That way you don't have to write out a whole bunch of them. But anyways, here are what all these pieces are. X sub k star is just some x value in the kth subinterval between x sub k minus 1 and x sub k. Okay, what does that actually mean? What that means is x sub k star is any x value in some subinterval between these two values. So maybe I'll pick right here, and I'll say x sub 2 star now, because it's in the second subinterval, is going to be some number in between 3/4 and 3/2. Now for us, what we did was we picked 3/4, it looks like. We picked 1. Here it is. It looks like for ours, right? So maybe I'll say, all right, x sub 2 star was 1. We noticed that we had a hard time with this 9/4. That was an annoying one to do. Maybe it would have been better if we'd picked something like 2. Right? 2 is within here. So maybe we could say, x sub 3 star is 2. The star is representing the fact that it's any x value in this subinterval, and then the k is like a counter telling you which subinterval it's a part of. And then delta x sub k is the width of the kth subinterval. The first subinterval is going to have a width of delta x1. The second subinterval is going to have a width of delta x2. Now for us, we're going to use a regular partition, meaning they're all going to have the same width. So this is the form that we'll use for Riemann sums. Notice all of these delta x's don't have an index in them anymore, a k counting which subinterval they're measuring, because we're going to assume that they're all the same width. We're going to pick a regular partition. That's pretty standard. All that does is just kind of shrinks the problem down a little bit, where there's not as many things that we have to keep track of. There's just one width that we're going to use for everything. So this is our definition of a Riemann sum. What we did up here in this example was a Riemann sum. Notice all of these areas are function values, where the input x was some x value in each subinterval that we picked, multiplied by this delta x, this width. For us, it was a constant width of 3/4, and then we just added those things together. So in our example, we did this. We found f of x1 star times delta x. That was our area of our first rectangle. F of x2 star times delta x. That was the area of our second rectangle. F of x sub 3 star that times delta x. There was the area of our third rectangle. And since we used 4 rectangles, we have this fourth term, where again, each of these were these areas that we called A1, A2, A3, and A4. So a Riemann sum is just a structured way of doing this. The nice thing is that there are a bunch of good results for Riemann sums that we'll use later on. All right, in general, we can pick any x value from each subinterval. The problem is that opens us up to a lot of extra choices, and sometimes that's great, right? If we go back to this example, we can say, where was it here? This 9/4 was kind of a tough x value to pick, right? Because it was a little hard to evaluate the function, and we got kind of this ugly answer for the area of that rectangle. Probably would have been easier if we just picked something like 2, because then 2 squared plus 2 is really easy. We can multiply that by 3/4, no problem, and everything works out a little bit nicer for the computations. So in some sense, leaving some choice is really nice. But you could imagine that if we had to do something with, I don't know, 10 rectangles, 15 rectangles, then making that kind of a choice for every rectangle might get a little bit dreary. So what we're going to do in general for our cases is we're going to pick these things formulaically. And here's how. We're either going to pick the leftmost x value in each subinterval, or the rightmost x value in each subinterval, or the very middle. So let me make this a little bit bigger. We'll go from 0 to 3. We'll cut this up into 4 pieces again. So I'll divide it in half and divide each of our pieces in half. And a left Riemann sum is going to pick these x values as our representatives. So for the left Riemann sum, we would probably use, I should probably write the x values on here, right? This one was 3/4, this one was 3/2, and this one was 9/4. So for the left one, we'll go ahead and use 0, 3/4, 3/2, and 9/4. For the right, we'll pick these ones. Notice that in each of our subintervals, I'm just grabbing the rightmost values. So here we'll use 3/4, 3/2, 9/4, and 3. And for the midpoint, we'll use values right here. So we'll go ahead and say, all right, halfway in between 0 and 3/4 is 3/8. Halfway in between 3/4 and 3/2 is going to be, oh boy, let me do some arithmetic in my head. This is going to be 3/8 plus 3/4. So that's 9/8. Is that right? Yeah. And then we've got 15/8 and 21/8. I think my arithmetic is right on here, but I am notoriously bad at arithmetic. So you can double check me on those. You'll notice just by me struggling through this that the midpoint one seems to be a little bulky, because not only do we have to find all of these partition values, the ones in dark blue, but then we have to find the values right in between them, the ones in light blue. So that's something that we can kind of think about. Before we do some of these examples, we'll just do this with a left Riemann sum, a right Riemann sum, and a midpoint Riemann sum. I want to show you visually what these look like, what the rectangles look like, so that we can get a bit of an idea of like what's going on with here. So here we can take a look at what these actually look like. So what I've got is this nice little applet. This function here is our x squared plus 2 function. I did scale it a little bit so we can see it all really nicely. And this is our left sum in red with 4 rectangles, so just like we did. So you can see what the partition numbers that we picked were. 0 defines the height here of this first rectangle. The x value of 3/4 defines the height of my second rectangle. We used 3/2 and 9/4 in that partition that we drew up. And if we click over here on the right sum, we can see what the right Riemann sum looks like. And you'll notice that all the rectangles now, they kind of like bump up against the graph on the right edge of the rectangle. Because again, we're using the rightmost x values from each of these subintervals to define the heights of each rectangle. You can see we have different approximations for the area, right? If I click on the left sum, it's much smaller than the right sum. The midpoint sum, you can see now the function crosses through our rectangle right in the middle of each rectangle. So 3/8, 9/8, 15/8, and 21/8 are the x values that we use to define the heights of these things. And this one seems to be a lot closer to the actual area. You can kind of see why, right? If you look at this left Riemann sum, all of the rectangles are too small compared to the function in this case. And in this case, the right Riemann sum, all of the rectangles are too big compared to our function. And so this midpoint sum seems to do a nice job of kind of like having part of our rectangle be too big and part of it be too small, right? So it kind of offsets the type of error that we have. We'll see, hey, look, this is actually pretty close to the actual area that we're going to be looking at here. We can show all of these things stacked on top of each other, and hopefully you can see it, the red underneath, the purple right in the middle, and then the blue on top. So this is what these Riemann sums look like. Hopefully that's helpful to see. Let's pop back to our notes here, and we'll just start going through our examples. And the nice thing is that we've got a bit of an answer key that we can use once we do this. So for this one, I want to go through this example, and I want to use a left sum. The way that we do that is we define it by L for left and 4 for the number of rectangles. So just as a reminder, we've got our partition. I always think this is helpful to draw from 0 up to 3. We're going to split it into a bunch of spots here. We know that the width, delta x, let me fix this, that was really ugly, is going to be the total width divided by the number of rectangles. So it's 3/4. So our first value here is 3/4, and then we had 3/2, and then we had 9/4. And again, for our left sum, we're picking these x values, the leftmost x value from each of these. So L sub 4 is going to be f of 0 times delta x plus f of 3/4 times delta x plus f of 3/2 times delta x plus f of 9/4 times delta x. And again, we're remembering that this is when f of x is equal to x squared plus 2. So you can go ahead and just plop these things in, figure out what we've got. F of 0 is 2. We've already found that one, times 3/4, plus f of 3/4, what's that? 9 over 16 plus 2, right? 3/4 squared is 9 over 16. Then we'll say plus 32 over 16, so this is 41/16 times 3/4. This is going to be 9 halves plus 2, so that's 9 halves plus 4 halves, so that's 13 halves times 3/4. And then this one I've already got, but let me do it again. 9/4 squared is 81 over 16 plus 2, so that's going to be plus 32 over 16. So what was that? 81 plus 32 is 113 over 16 or something like that, hopefully. What I normally do is notice that the cool thing about using a regular partition where all of our widths are the same is that we can just factor that out. So it's really 3/4 times 2 plus 41/16 plus 13 halves plus 113/16. I don't have a calculator with me, and I don't need one. This is a calculus class. We should be able to do arithmetic. I'm going to just put these all in terms of something to the over the 16th. So this is 32/16 plus 41/16 plus, what's 8 times 13? That is 104/16. You can check me on that. And then 113/16. We should be able to add this stuff up, and then hopefully multiplying by 3/4 won't be so bad. 32 plus 41 is 73. Plus 104 is 177. And so we are at 290 over 16. So this is 3/4 times 290/16. Let me just double check that really quickly. Yeah, I think that's right. All right, and then I might notice that we can cancel some stuff, kind of, right? I'll call this 2, and I'll call this 195. If I divide both of those by 2. Oh, no, that's not right. Oh, boy, that was going to be a problem. This is 145. There we go. 290 divided by 2 is 145. And this might make things a little bit easier now to multiply. 2 times 16 is 32. 3 times 145 is 450 minus 15, so that's 435. Is that right? 3 times 5 is 15. Yeah, that's going to be fine. And then I will grab a calculator to see if I can figure out what this thing is. 435 divided by 32. I've got, well, I won't need to say approximately. I'll give it to all the decimal points. 13.5938. Hopefully that's what we got over here. Oh, no. We got something different. Well, that's no good. All right, let me figure this out. All right, here it is. So this one here is wrong. Because 3 halves squared is 9 over 4 plus 2, that's 8 over 4, so this is 17/4. Whew. So let this be an advertisement for why Riemann sums are annoying to do by hand sometimes. Okay, so then this was putting everything in terms of 16ths, right? And I got to change my 17 over 4, 17 times 4 to put this over 16 is going to be, I'm blanking. What's that, 68? Yeah, that's 80 minus 12. All right, so now everything else is going to change. Let me fix this. All right, I think I cleaned up all my arithmetic errors on here. So I changed, again, just to remind you, I had this function value wrong here. And so that changed this value, and that changed this to 68/16. That changed our total that we were adding up. And so then from here on out, we end up with 381 over 32, which is 11.90625. I probably should have checked this before. Okay, yeah, we're good, because this left sum rounds it to 4 decimal places. Perfect. All right. So what I want you to do now, oh boy, we're asking a lot, right? What I want you to do now is to go ahead and use the right sum. But I'll give you a couple of hints. We'll set some stuff up together. So we're going to call this R sub 4. Let's draw out the partition from 0 to 3. We'll cut this up again we've got 3/4, 9/4, oops, sorry, 3/2, and then 9/4. Delta x is again 3/4. That part is all the same. But now, instead, we use the rightmost x values. So, go ahead and write this out. And I'll give you a little nice tidbit to see once I've got this written. Because we don't have to do all of this over. Because what you'll notice is that this Riemann sum is only different from this one by this term. We still have the f of 3/4 times delta x, the f of 3/2 times delta x, and the f of 9/2 times delta x. But we've swapped out 0 for 3. So you should be able to do this one pretty easily. So take a minute, pause the video, jump into this, see if you can just kind of crush through the computation on here, and then we'll check our answer in a second. Go! All right, so you should have something like this. Again, the only new value that we've got is this 11, which turns into 176/16. And then you can just add everything back up like we did before, and we get this new approximation of our area. Cool. If you want, you can do this using the midpoint one. I'm fine without doing that, though, altogether. So go ahead and do it, and if you'd like to check your answer, you should get approximately 14.8594. Now, that might be rounded to 4 decimal points, so it might be like 935 or something like that. But go ahead and do that and see what you get. Now, here the actual area is 15, and so our question might be, how do we do a better job? Well, one of the answers seems to be these midpoint sums, right? The midpoint that we had seemed to be a better guess for our area than the left or the right. Now, that's maybe a frustrating answer to hear because the midpoint sums so far are more complicated, right? It took us a little bit to find those partition values, and if we go back to these slides and we go back to setting up that partition, these are the x values that we're going to plug into our function. Oh, this is just going to be a hassle to try and square all those and add 2 and to get these ugly fractions. I don't want to do that. I'm sure you guys don't want to do that. And so what we'd like to do is answer this question a little bit differently. Instead of saying use the midpoint one, maybe what we could do is go back here and just use the left sum one and maybe do like 25 rectangles. Because, hey, look at this. Our left sum is like 14.5-ish. That's pretty close to our actual area. Or the right sum, which isn't that hard to do if we know how to do the left. It's only different by like one function value. That's going to be 15.5-ish. Again, notice the midpoint is a really nice approximation here. But if we want an even better approximation, what if we did like 50 rectangles? Now that would be a pain to write out. And so that's where you might notice that we end up using that like summation notation, something like this. We'd say, all right, this is what that might look like for 50 rectangles. And we'll say x sub k star delta x. And we try and write up some nice little pattern or formula so we don't have to write out 50 terms added up next to each other. And we could do even more. The one that I built goes up to 75 rectangles. And you'll notice we can barely even visually see the difference between the left and the right sums, right? They're so close to each other. So these are really good approximations. All right. So if we get better approximations by using a bigger number of rectangles, essentially more rectangles, increase n, then maybe if we want to get a perfect approximation, wouldn't it make sense to look at a limit as n, the number of rectangles, went to infinity of this Riemann sum structure? And notice if we do this, delta x gets tiny, right? because delta x is b minus a over n. And if we let n get really big, then this whole thing is going to go to 0. So we have infinitely many, infinitely thin rectangles. That's going to be something that we'll mess a little bit with later. We'll probably do one of these limits. I think everyone in Calc 1 needs to see this at least one time. But then what we'll do is build towards something called the fundamental theorem of calculus, which will help us do this, and it's going to connect back with antiderivatives. So like at the beginning of this video, I said there is a connection with antiderivatives. We will get there. That's going to be when we hit the fundamental theorem of calculus. So that's what we've got for our video here. We can use Riemann sums. It's really just rectangles added together to get some areas. All of these are approximations until we build up to this limit idea.